In lecture 30, we talk about semiconductor p-n junctions. We first talk about equilibrium band diagram of p-n junctions, and we specifically talk about how p-n junction will behave under bias. So first, students should be able to draw the equilibrium band diagram of a p-n junction and identify the depletion or space charge region. So this shows the energy levels, particularly the Fermi level location within the semiconductor band gap before forming the p-n junction. And again, as we talk about in metal semiconductor contact on the thermal equilibrium, we will have a constant Fermi energy. So in this case, you need to tighten the phase and then push the Fermi level down on the semiconductor N-type semiconductor side and push the Fermi level up on the P-type semiconductor side. So eventually you have band bending occurring in both semiconductors. So the key to draw the band diagram, equilibrium band diagram, is that you have a constant Fermi energy throughout, and also away from the interfaces, the carrier concentrations will remain the same. So the relative location of the Fermi energy with respect to the conduction and valence band edges will remain the same. And again, as the Fermi level or the valence band bends away from the Fermi level in the P-type semiconductor, we have reduction in hole concentration. That's partially the depletion region. On the N-type semiconductor side, when the conduction band edge bends away from the Fermi level, we have a depletion of electrons. Again, that's part of the depletion region. So we have depletion region on both sides of the semiconductor p-n junction. And the band bending occurs on both sides as well. So the second student learning outcome is that the student should be able to calculate the values of total band bending, the building potential, and the total depletion region width. So to calculate the band bending, again, understand that the band bending is needed to align the Fermi energies. So how much the Fermi energies are misaligned before making the contact is how much you need to bend the bands to align them. Okay. So to calculate that, you can take the total band gap, start from total band gap and take away the Fermi level difference from the valence band edge in the P-type semiconductor or the conduction band edge in the N-type semiconductor, and then you get the middle portion. Or you can introduce the intrinsic Fermi level and calculate how much the Fermi level is off from intrinsic Fermi level on the P side and N side and add them up. Okay, so either way, that will get you the total band bending. So just introduce all those 4 different things. You can calculate the total band bending being the addition of the Fermi level difference from the intrinsic Fermi level on 2 sides, that's these 2 quantities, or you take these 2 little pieces off from the total band gap. Okay, so the calculation is based on using the equations that relates the Fermi level location to the carrier concentration in the bands, or you can relate the carrier concentration to the intrinsic carrier concentration by looking at the difference between the intrinsic Fermi level and the actual Fermi level using these 2 equations. So with the math that's being shown here, eventually you can calculate the band bending or the VBI being given by this equation. It's related to the doping concentration on the 2 sides. Also, you can look at the majority and minority carrier concentration on either side, and then in this case, you can basically look at the whole concentration contrast from the P side to the N side, or you look at the electron concentration going from N side to the P side. And by looking at this ratio, you can also obtain the band bending, because remember, the band bending is the bending both in the conduction band or the valence band, and so how much the Fermi level is off from the conduction band edge difference, the difference across the 2 sides will give you the band bending. That's really being shown in these 2 equations. And also for the depletion region width, again, you will have depletion on both sides of the p-n junction, and overall, it's also related to the doping concentration, but also related to the band, to the building potential that we obtained just previously. So the next student learning outcome is that you should be able to describe the polarity of the voltage bias and changes in the band bending and depletion region width on the forward and reverse biases for the p-n junction. So we have this band diagram under equilibrium. The total band bending is given by QVBI, which is determined as we shown on the previous slide. If we apply a forward bias, again, as we talk about in metal semiconductor contact, this forward bias will partially compensate for the building potential. So that results in a reduction of the total band bending. And this if you reverse the polarity, you will get to the reverse bias, and you will increase the band bending. by whatever voltage you apply. So in general, if you just say that there's a voltage applied, then if it's positive, then it's forward bias, it's reverse, it's negative, it's reverse bias, and the total band bending is just VBI minus V. And also, this VBI minus V will replace VBI in the equation for the depletion region width. So on the forward bias, this depletion region width will be slightly reduced, and on the reverse bias, this depletion region width will be increased as being shown here. Finally, you should be able to describe the rectifying behavior of the IV characteristics of PN junctions. This is so-called Shockley diode equation. So the overall behavior is the same as we have seen in the metal semiconductor contact in terms of the IV characteristics. But obviously now in this case, we need to consider the transport of electron and holes together in the same system. And for both electron and holes, we are going to have a diffusion because we have high concentration and low concentration, basically a concentration gradient across this junction. And also, since we have electric field in the depletion region, we're going to have drift motion of the carriers. So on the forward bias, we will reduce the band bending, so that allows the electrons to go across the interface very easily, exponentially increasing. So on the other side of the depletion region, we're now going to have excess of carriers. So the electrons coming from the N-type semiconductor to P side will become minority carriers, and then since we build up so many electrons, they will slowly diffuse into the neutral P side and eventually combining with holes coming from the electrode. So now we have electron diffusion current, and then we have a hole diffusion current to match up. The total will remain constant since we should have a constant current running across the junction. On the other side, holes transporting in from the P side to the N side will give you a very high excess minority carrier concentration into the N side, and they will diffuse into the neutral N side and then forms the whole diffusion current, and that will be compensated by electrons coming from the electrode. So overall, you're going to have a constant current, which is going to be very high on the forward bias condition. On the reverse bias, we're going to have a deficiency of carriers on either side because now we have an increase of band bending that decreases the likelihood for electron holes to drift across. That's why we have a depletion of carriers on the edges of the depletion region compared to the equilibrium situation. So the reverse bias current will be a lot lower. And that gives you the Shockley diode equation given by here. And this JS, again, is the reverse bias saturation current. So the forward bias is going to be exponentially increasing. The reverse bias will saturate to a relatively low level. So the overall behavior is the same as we have seen in the Shockley junction. It's just that the nature of the reverse bias saturation current density will be different. In this case, it depends on diffusion of both electron and holes into the neutral side, as these are the minority carriers. So again, the rectifying behavior is such that the current only goes in the forward direction. On the reverse bias, it's basically nothing. So you can actually calculate the so-called rectification ratio by looking at the ratio of the forward to reverse bias current at a particular voltage. And obviously, this rectification ratio is very, very high. So this is the end of the review.